Hi guys. So good afternoon. Welcome to Lab 5. I hope I'm audible. If not, do tell me. So the agenda for today is to uh, go over transformers. So I don't think Sir has covered transformers yet in the lectures. So first, what we'll do is I have a small presentation that I made like for something else, but then it's just about transformers, so we'll have a quick look at what the basics of it, so that otherwise there's no point, right? Um, so we'll do that first, and then we'll also go over how you can train a basic maybe. The problem with transformers is that these models are pretty huge, and typically they require hours of training, if not days, and so it's not really possible to demonstrate something real time in like within the span of a 2 hours lab. So what we're gonna do is we're gonna just fine tune a pre-trained transform model on a data set, and we're gonna use a library called Hugging Face. Some of you guys must be familiar with it. um, right, so that's the agenda for today. So first I'll start with the tiny presentation that I made. It's a very basic presentation. It's just about what transformers are, so that you have a basic idea. And do stop me if you have any questions anywhere. Because so this time the problem is, because I'm the lab is we're not going to write too much of code, because we're going to use Hugging Face. 90% of stuff is already built into Hugging Face, so like we'll pretty much have to write like I don't know, 20 lines of code. So there's not really much that I can ask about the library or the code implementation itself in this lab. So the questions will be more towards very basic questions about transformers. So it's important that you pay attention during the presentation as well. Okay, so I'll present it, and please do let me know if my voice cuts out or something happens. uh, right, so as I was saying, this is a presentation that I made like about a year ago, but then it's still useful because the basic idea of transformers remains the same. So the basic building block of transformer is something called self-attention. So what is self-attention? Self-attention is a sequence-to-sequence operation. So what does that mean? It just means that you given a sequence, it returns a sequence. So you given a sequence h1, h2, h3, it returns a sequence y1, y2, y3. That's it. That's all self-attention is. And how do you get this? So once you given h1, h2, h3, how do you get this y1, y2, y3? You get that using a weighted average of these. So assume you want to calculate y2, then what you do is you multiply certain weights with h1, h2, h3, and so on, and then you add them together. That's it. So this is okay. So I think this might be I don't know how to move this, but yeah, I mean, so um, right. So imagine you want to calculate y2, and then what you'll do is you'll have weights w21, w22, w23, and so on. You multiply that with h1, h2, h3, and so on respectively, and then you add them together. That's it. That's the self-attention operation basically. And each of so x is k-dimensional, and so is y. Y is also k-dimensional. You probably can't see it here because of this thing, but yeah, k is also y-dimensional. Yeah, so for example, if you're calculating y2, then you have four weights. So assume you just have h1, h2, h3, and h4. So then you'll have four corresponding weights: w21, w22, w23, and w24. You multiply them together, you add them, you get y2. This is when you're calculating y2, and similarly you'll be calculating y1, y2, y3, and y4 corresponding to h1, h2, h3, and h4. Right. So it's just a linear operation. I mean, it looks linear right now, so you'll see why it's not, but it's linear in the sense you're multiplying weights and you're adding them together. But then where do we get these weights? The key point is that these weights are not learned weights. Rather, they are generated from the input itself. So you have h1, h2, h3, h4. So you generate these weights from the input itself. So how do you generate it? Yeah. So the weights are not parameters, like it's in a neural network. Instead, they are derived from the input sequence. Input sequence being h1, h2, h3, h4. So the weights are calculated using, so this is a dot product. So I mean, imagine this vector is vertical. So when you do a transform, it becomes horizontal, and then you have this vertical vector again, and you multiply it together. So it's just like a dot product. What the basic dot product that you know. So I'll give you an example so that's clear. So for example, if you want to calculate W21, so you take H2, you take its transpose. So now so if it was k comma 1, now it's 1 comma k, and this is okay. That does not make sense. If it is 1 comma k, now it's k comma 1. And then if this and this will remain 1 comma k, so you multiply them together and you get the weight W21. And similarly, you can calculate for W22, W23, and W24. The key point here is that the weights are not learned. The weights are generated from the input sequence itself. So yeah, right. So but then these aren't the final weights because these won't add to 1. So what you do is so usually what do you do? So usually when you get a normalized scores, what do you do to make them add to 1? You apply softmax. That's what you do here. It's here also. So you take all the weights. Yeah. Is that a question? No. Okay. Uh, I thought I heard somebody. Okay. So you take these weights that we just made, right? You take these weights that we just made, and you apply softmax over them. So all of these weights, W21 plus W22 plus W23 plus W24, will add to 1 after you apply softmax, right? So this is just the softmax operation. You probably like pretty clear with this now because we've done this like in 3 labs. Right. So for example, if you're calculating W21, you take the W21 prime that we calculated using H2 and H1. So you took H2 transpose and you multiplied it with H1, you get W21 prime. And similarly, you get W22 prime, W22 3 prime, and W24 prime. But then you apply softmax to it, and effectively what happens is all of these add to 1. W21 plus W22 plus W23 plus W24 will eventually add to 1. Right. So this is a basic illustration showing. So I've taken this figure from an amazing blog post by by a researcher called Peter Bloom. So he has this blog post that he's written about transformers, which is amazing, and I would recommend that you guys read it if you haven't already. Yeah, just remind me to send the link if you guys want it. I can send the link towards the end of the lab. Okay, so what is happening? So we assume we are calculating y2. So how will we calculate y2? We will calculate y2 by using w2. So we'll have a weight w21. We'll multiply it with h1, right? W21 times h1 plus w22 times h2 plus w23 times h3 plus w24 times h4, right? And how do we calculate this w21? You calculate this w21 using h2 and h1, right? So w21 you calculate first using h2 transpose times h1 and so on. And yeah, there is the softmax, which is not shown here, but so W21 is calculated using H2 and H1, and similarly W22 is calculated using H2 and H2, and so on. Right. So that's basically what this diagram is showing. So thing to note here, the extremely important thing that you have to note here is that every input vector is playing 3 roles. Right. You can see every input vector in 3 places. The first place that you can see is here in the bottom. Right, as the input sequence itself, you can see it. The second place you can see it is here, right? So in this case it's h2, but if when we're calculating y1, there'll be h1 here. When we're calculating y3, there'll be h3 here instead, and so on. So there's the second role that these vectors are playing, and this third role that these the vectors are playing here, right? So there are 3 different places, 3 different types of roles that these input vectors are playing while doing this calculation. While doing this calculation. So that's all self-attention is. Even in modern transformers, like that's pretty much the basic version of what self-attention is. So what is the intuition for self-attention? So I don't know if you guys have done the ML course. So but then like if you have like a basic movie recommender system, what usually happens is you have a feature vector corresponding to the movie. You have a feature vector corresponding to the each user. So how do you determine if this movie is a good recommendation for this user? So what you do is you take a dot product between their I'm sorry. You take a dot product between their feature vectors, right? And so this dot product that you get is kind of a score that tells you how good of a recommendation this movie is to this user. And depending upon the score that you get, if it's big enough, you recommend this movie to this user and so on. So it's kind of similar to what is happening here. So like if corresponding to, so you have an input x1, x2, x3, and x4. So when you're calculating y2, you are doing this multiplication, right? You're doing x2 transpose times x1. So it's kind of like you're calculating the similarity or the relationship in data between h2 and s1. Here you're doing it between h2 and h2. Here you're doing it between h2 and h3. So you can think of it like you are kind of extracting relationships that exist in data, right? Similar to how you're doing it here. Like there is some feature vector here and there's some feature vector here, and you're multiplying them together to get kind of a similarity. So the same thing there, but instead of doing it between two different types of feature vectors, you're doing it between the different tokens in the input sequence that you have passed in. Right. Okay, that's easy. Yeah, yeah, yes. Uh, so when you multiply this thing, oh, so wait, I didn't understand the question, but what are you talking about? Oh, this thing. Oh, okay. So yeah, I don't. Right, right. So you're talking about this thing. Yeah. So uh, how do you get a single value? It will be k by k, right? If it's k by one and one by k, it'll be a k by k. Hj should be one by k. Did I put k by one? Where is it? Uh, oh, okay. No. Right. Product will be k by one because you want the output to be k by one as well. But you understand, right? Like if I made a typo mistake, like just ignore it. But you understand what the like, because the input dimension and the output dimension should be the same. The weight has to be k by k. It can't be one by one. Okay. So where were we doing? Yeah. So we were talking about the intuition behind it. So okay. So now the problem is, let me go back to full screen. Right. The problem is, so far, did you see weights? I mean, you did see weights, but those weights are like deterministic, right? You did not see any learnable weights that you can learn through backpropagation and optimization algorithms. Like none of this is there here yet. Like there is no scope for learning weights anywhere yet. But then, if there are no learnable weights, it's not really a deep learning architecture. So like where do we include the weights? So that is where this roles that each of these vectors play becomes important. So I told you that each of these h1, h2, h3, and h4 plays three roles. The first role that it plays is here, right here, where it's acting as kind of values. And there is this role that it plays where it's kind of querying. I mean it's not really the best nomenclature, but like these guys, the original transformer paper guys have used this nomenclature in. So it's kind of similar to how you query a database. You take h2 as a query and you query the entire database, which contains h1, h2, h3, and h4. So these h1, h2, h3, and h4 here, they play the value of some a kind of key, right? So there's a query, there's a key, and there's a value. And I mean, yeah, it's it's not the best names that you could give this, but like it kind of makes sense if you think about it. Like you're querying. So in order to get y2, you are querying all the keys, right? h1, h2, h3, and h4. And what is the query here? The query is h2. So you query it and then you multiply it out by a value. So here these vectors are playing the value of value vectors. Here they are playing the value of query vectors, and here they are playing the value of key vectors. Right? This becomes important when you want to make the whole thing learnable. Right. So right now self-attention is very weak. It's a very deterministic thing. Like there's no learning involved, and so its scope is very limited. So if you want to make it more and more powerful, as is what is done in transformer models right now, you have to add have some learnable weights. So how do you introduce this learnable weights? That's the first part, the query key and the value vectors. So let me go back to this again. So here we were passing in h1, h2, h3, and h4. So instead of this, what you do is, so here I told you they are playing the role of value vectors. So instead of passing in h1, h2, h3, h4, what you do is you apply a wv, you apply a learnable weight w to each of these h1, h2, h3, and h4 to get v1, v2, v3, and v4, which are the value vectors. Similarly, here, what is the role that is played by h2? It's playing the role of a query vector. So you take a big matrix WQ, right? WQ is a learnable matrix or a learnable weight. It's not a single weight, it's a set of weights, it's a matrix. You take WQ, you multiply it by h2 to get a query vector Q2. Right. Similarly, when you're calculating y1, you'll need q1, and similarly, when you're calculating y3, you'll need q3, and so on. And here I told you that these vectors are playing the value role of key. They're playing the value of key. So instead of directly passing in h1, h2, h3, and h4, you first generate key vectors from it. So how do you do that? Again, you take a big matrix wk, you multiply it by h1, h2, h3, and h4 to get w1, w2, w3, and w4, and then you pass those here instead. So it will be v1, v2, v3, v4, q2 in all these places, and then it will be k1, k2, k3, and k4, and all of these have been generated using three learnable matrices: wq, wv, and wk. So that's what I've written here. So you take wq, you multiply it with hi, you get qi, the query vector. Similarly, you get the key vector, and similarly you get the value vector. Right. So now what has happened here? So the most important thing that has happened here is that this WQ, this WK, and this WV have learnable parameters. So once you have learnable parameters, the thing is that now you can do backpropagation, you can calculate gradients, you can apply, I don't know, stochastic gradient descent, some optimization algorithm to update these weights. So that makes this whole thing more powerful in a way. Right. So everything else is the same. Everything else is exactly the same. So instead of doing say H2 transpose H1, you do Q2 transpose Q2 transpose K1 to calculate W21, and then again you apply softmax like I was discussing earlier, and then again you add them all together to get the weight, your final weight. It's very easy. Like it's exactly the same thing. You're doing a linear transformation. It's just that this time there's a weight that you are that is present. So when you're calculating Q, there's a weight. When you're calculating K, there's a weight, and when you're calculating V, there's a weight, and all of these are learnable. Like, is there any question? Please do ask. Okay. Right. The training. So if when you're doing training, what will be the weights that you'll be updating will be WQ, WK, and W. Right. It can be anything. So transformers are like it's basically so transformers are, they can learn anything basically. Uh, so you apply transformers for like object detection, semantic segmentation, and so that's all like computation stuff. You use it for NLP. Look, so it started with NLP. You can do language learning. Like, so last time we did character level prediction. If I remember correctly, we did character level prediction with RNNs and LSTMs. You can do that with transformers. You can do semantic analysis, which is what we'll be doing today. You can do all kinds of things. So depending upon what you're doing, the input will be different. So if you're doing like image tasks, then the input will be like patches of images. Uh, if you're doing NLP stuff, it might be characters, it might be words, like tokenized words or characters that you're passing. It all depends on what it is that you're doing and what it is that you want. Yeah, it is very flexible, right? So, right. So this slide we already did. So it's exactly the same as earlier. It's just that now instead of having X everywhere, you have specialized vectors for each of these things, and they are generated by using some learnable matrices or weights. So now a slight modification that you have to make though is that instead of just multiplying, you have to divide by the root of the dimension. That's just it's not really important. It is important, but it's not really important in the big picture. The reason you do this is just because when you're applying softmax is like really sensitive to big numbers, and it will slow down training if you have like really big inputs to softmax. So what you do is you divide everything by root of k being the dimension. You know what k is the dimension of the input. You divide everything by root of k so that you scale down the whatever you're going to input to the softmax. It's just a minor tweak. It's not really important, but I wanted to include it because everybody does this. So right. So now this is the big picture now. So instead of having x's here, you have q, k, and v. You divide by root k, and then you apply softmax to so that the weights add to one, and then you multiply the weights with instead of multiplying with h, now you multiply it with v, the specialized vectors corresponding to h1, h2, h3, and h4, and then you add them together. You get the output y. That's it. Yeah. So this is pretty much it. So this is single head. This is something called single-headed attention. So this is self-attention. It's called self-attention because you're kind of attending to yourself, right? Like so when you're calculating these weights, you are using the input to generate the output. So in the sense that when you're calculating y1, uh, you are how do you generate the weights? You generate the weights using the inputs. You generate the uh, y1 using h1, h2, h3, and h4, and the weights are like kind of similarities between the individual tokens. So that's why it's called self-attention, because you're attending to the self. And so here we did a single. So wait, let me go back to this. So this is a single attention operation basically. So when you're calculating y2, you're doing a single set of linear transformations on these h1, h2, h3, and h4, and adding them together to get y2. So it's called single-headed attention, meaning that you only do it once. But as with everything, people realize that the more the better. So you can do it multiple times. So in order to calculate y2, instead of having like a single, instead of doing this once, imagine you do this 4 times, or like say 12 times. So then you will have 12 outputs y12. Instead of having one y2, you'll have 12 y2s, and then you can apply. So one thing you can do is you can apply fully connected network to reduce its dimension back to k. That is one thing that you can do. Because, I mean, you have always seen that, right? Whenever we have too much dimension, we always apply a fully connected network so that we reduce the dimension to whatever is desired. Right. Yeah. So that's pretty much it. I don't know. Yeah. So wait, I'll show how that is done as well. So it's called multi-headed attention. So the reason, wait, I'll discuss the reason why we have to do this. So so let's imagine that we are calculating the output corresponding to this. So assume that this is our input sequence: h1, h2, h3, h4, h5, and h6. And say we are calculating the output corresponding to, say, biryani. So let's say the output is y6 that we are trying to calculate. So when you're trying to calculate y6, right, when you're trying to calculate y6, what will you first do? So you'll first generate weights: w61, w62, w63, w64, w65, and w66 you'll generate. You multiply that with each of them. You multiply, so w61 times, instead of h1, that will be v1, but let's assume it's h1. So w61 times h1, w62 times h2, and so on. You add them together, and you get y6, right? That is what you do. But imagine instead I had this pretty nonsensical sentence, right? And you wanted to calculate the output corresponding to y6. Will there be a difference though? There will not be a difference. Why is that? There will not be a difference because you're adding, so you're summing up, right? You're summing up the sum. You're summing up the individual products, and there is no order to it, right? So this is why attention is permutation equivariant. Equivariant meaning that it doesn't matter. So like if you shuffle it around, the output corresponding to biryani will still remain the same, right? Which is a problem because, like, if you think about it, these two sentences mean like wildly different things. So first thing is fine, second thing is not. So like uh, so it is a problem. So it is a limitation of the architecture itself if it is not able to distinguish between these two. Because like if you're calculating the output corresponding biryani, and if it's the same in each case, then like this clearly a problem. And so the problem is, it's unable to attend to more than one thing. So like when it's calculating the output corresponding to biryani, so like say it is as attending to abhijita, so it's attending to chicken, and you're adding all of this together, and it's kind of like you are losing information. So to solve that, you do something called multi-headed attention. So instead of having just like like I was discussing earlier, instead of just having like one output, you have, say, like t outputs, like say 10, 12, 24, I don't know, whatever, 24 outputs correspond. And how do you do that? So instead of having, so how did you calculate the output? You calculated the output using these weights, right? using these weights. So we had a, if you remember, we had a W. Wait, where is it? We had a WQ, WK, and WE. So instead of having one WQ, WK, and WE, we'll have a set of them. So we'll have a set of, say we have 12 WQs and WKs and WEs, which are all learnable. And so what happens? So because you have 12 WQs, WKs, and WEs, so you will be able to generate 12 QI, KI, and VI corresponding to each HI, all H1, H2, H3. And using these 12 sets of vectors, you will be able to generate 12 outputs. And then you can use all these 12 outputs. You take these 12 outputs and then you can reduce them to a single output using a fully connected network or whatever you want to do. So instead of having just one set of meters, WQ, WK, and WE, we have T sets of it. And so because we have T sets of it, we'll have T sets of QI, QGen, QI, KI, and VI for each HI. And yeah, therefore you'll have T sets of outputs. Yeah, so that is called multi-headed attention. So it's just I mean, it's not really important. It's just the upgrade. You can think of it as an upgrade over single-headed attention, that you're doing it multiple times. And I mean, the basic reason. What is the basic reason here? The basic reason that it's working better is because you have more weights. You have more learnable weights, so the model is able to look at, like, so in one head, in one of the 12, it will look at one thing. In one of the other, maybe in the second thing, it will look at something else. So in the first thing, say it focuses on Abhijit, and maybe in the second thing it focuses on chicken, and maybe in the third thing it focuses on loves, and so on. So instead of having to like focus on everything all at once, you can focus on different things in each of the heads. So that's why it's called multi-headed attention. Yeah, that's it. So that's pretty much it. Like, that's all the math that we're doing today. Yes, somebody asked a question. Um, I'm sorry, I didn't understand. What are you asking? Right. Yeah, right. Okay. So when you're calculating, say, Y-sits, so when you're calculating Y-sits, what are you focusing on? Like, what is your model focusing on right now? So it can focus on any one of these. So say it's focusing on Abhijit and chicken. So it needs the fact that Abhijit is eating chicken biryani. So I'm not eating mutton biryani, I'm eating chicken biryani. So the fact that I'm eating chicken biryani and it's me who's eating chicken biryani, all of this information it's going to focus on when it's calculating Y-sits. But imagine you have, and it'll happen here also. So if chicken loves to eat Abhijit biryani, here also it has to focus on Abhijit and chicken at the same time. So imagine instead we have say 4 heads. So the first head, it will focus on chicken, and the second head, it will focus on Abhijit. And so it will be able to, say the first head learns. So when you're training it, say the first head learns to identify the subjects. So the subject here is Abhijit, right? And so because you have a single head that focuses on the subject, say it focuses on subject, it's not as simple as that. But let's say that the first head learns to focus on the subject. And so when you're applying the first head, in this sentence it will focus on Abhijit, in this sentence it will focus on chicken. And in the second head, say it focuses on whatever, so in this case chicken biryani, so like it's a type of biryani. So let's focus on this let's say the second head focuses on this. And so the first case, the second head will focus on this, and the second case, the second head will focus on this, right? And so there's a semantic difference, right? So if the first head is learning to focus on subjects, then the model gets to know that the subject here is Abhijit and the subject here is chicken. Yes, it is, right? Because now it is, I mean, if not perfectly, it's able to like distinguish between the fact that it's chicken biryani and it's not something else. Okay, cool. Right. So like we have discussed everything that we need. Wait, somebody asking something? So I didn't mention that. So like I was just taking an example. Like, I don't know, maybe you're translating this to French. I don't know. You can do whatever you want on the input sequence. I'm just looking at the input sequence. It doesn't matter what you're eventually gonna do. Eventually, I don't know, whatever you want to, like, you want to translate it to Hindi, you want to translate it to French. It doesn't matter. Like eventually, like this limitation applies to any kind of transformer, I mean, like any kind of self-attention, right? Like irrespective of what you're doing downstream, this limitation applies to all of these. Like so imagine this limitation that applies to a convolutional neural network. It does not matter what output it's producing. It will apply to any kind of convolutional neural network that you're trained, right? So I just wanted to point out the limitation. So this will apply to like every self-attention that you see, single-headed self-attention. Now that we have multiple heads, we kind of allay this limitation, but yeah, it's still there. Okay, so we have discussed everything that we need to discuss transformers. So what all did we discuss? We discuss what self-attention is. It's just an input to output sequence, so operation. So you take an input, so you return output. And how do you do this? We discuss how we calculate the weights, and we discuss the intuition behind it, like how you identify like similarities or like representations uh, within the data itself. And then we upgraded self-attention using two things. First, we had added like learnable weights, and the second thing that we did is we upgraded single-headed attention to multi-headed attention, so that it's now a bit more uh, powerful in a sense. So these are all that you need to do transformers. So transformers, let me go back to full screen. So transformers, so this is a transformer block. So similar to how you like have like a convolutional network block, this is a transformer block. And this is I mean, so there are, so if you look at like conferences this year, there are like hundreds of papers based on transformers, and there will be like a huge variety on the kind of architectures that people do. So it's naturally impossible to like look at all kinds of architectures that people do, but like a basic version of transformers will always have two things. It will have the self attention that we discussed, and it will have MLPs. Okay, and how does it work? So you take in the input, you apply your self attention, everything that we discussed so far. It can be single headed, multi headed, whatever. You apply multi headed attention, okay, and then you apply layer norm. And it's a kind of normalization. I'm not sure if sir has taught it in class. You know batch normalization. This is layer normalization. So instead of like average, so if it is batch normalization, what would you do? You would average over the batch, right? So instead you average over like the layers instead. So you average over a single layer. That's layer normalization. It's not really important. It's just so there's a reason that they've used it, but it's not really important per se. The important thing is that you apply self-attention first, and you apply normalization, and then you apply an MLP, and you apply normalization. That's it. That's the transformer block. So you should have this imprinted into your brain that the basic thing in every transformer architecture, irrespective of all the fancy things that they might be doing, like each author will be doing each kind of thing, but then they'll all have self-attention, and they'll all have some kind of an MLP or something here. Like it will be some learnable network. I mean, typically it's an MLP, and MLP meaning fully connected networks, multi-layer perceptrons. And the important thing here is that these are not different MLPs. You're just taking the same MLP and you're applying it to each of these. So like these are common weights. Don't think that this is a different MLP and this is a different MLP and this is a different MLP and so on. This is the same MLP. It's just that I mean the picture shows it like multiple times because like you're applying it independently each of these, but the weights are shared. Meaning it's the same. It's the same thing. It's kind of like in RNNs how you like split it out into different time steps, but it's effectively you're just passing it again and again. So the same thing. Similar to that, it's you have an MLP and you're passing each of these input tokens through it. The output after self-attention, y1, y2, y3, and y4, you pass through the MLP, and you apply layer normalization. Cool. This is not important. I mean, it's not really important for the lab, but the problem with self-attention is that its complexity is big of n square, and the reason for that is the dot product that you saw. The dot product is, so imagine you have a k-dimensional vector, you're doing a dot product, right? So with itself, so that's square complexity, and yeah, it's harder to train transformers than say convolutional neural networks or something similar. Because of the, I mean, one reason is because of the huge number of parameters that we'll have. Yes, somebody has a question. No, no. Okay. Let me go back. Right. This is not really important. I'm not asking this in the quiz, so you don't have to worry. And the advantages of transformers are like multitude, because if you look at any machine learning or like computation or any kind of conference that deals with like machine learning, you'll see that everybody's using transformers. Like for the past year and this year also, that's the case. And the reason for that is because transformers are extremely versatile models. Even like unsupervised, in the field of unsupervised learning, it's extremely good. And the reason for that, there are many reasons for that, and we'll not discuss that. But then a very important advantage with transformers is that it's very easy to parallelize. And parallel computations are what GPUs are extremely good at, and that is also what transformers do the most. Like when you're calculating h1, h2, and h3 and h4, you're like multiplying h1 with h2 and h2 with h3, and all these multiplications that happen in parallel. You can do everything in parallel. Like all of these you can do in parallel. The self-attention operation is extremely parallelizable, so that's why uh, that's the biggest advantage in terms of performance itself. uh, yeah, that's pretty much it in terms of the presentation. So if you have any questions, please do ask, otherwise we can go to the lab. Okay, I'm assuming nobody has any questions. So for this lab, primarily because like implementing a whole transformer from scratch is not possible within 2 hours. What we're gonna do, and plus it's not recommended. It's not recommended. Like even if you can do it, don't do it. Uh, so there's this library called Hugging Face. You must have heard of it. Like it's super popular now. Uh, so this is a platform where you have access to models. You have access to like thousands of models. So like see 80,000 models and pre-trained models. So like that's more valuable than just getting models. So like pre-trained models. So these are all trained on like some model or the some data set or the other. You get access to the you get access to like thousands of pre-trained models from different people. So you can also upload your own model if I'm not wrong. And you get access to data sets and tens of thousands of data sets. And you also get access to something called spaces where you can play around with like other people's models, like the so you can like pass in an image and like maybe so you must have heard of diffusion, right? So wherein like you pass in text and it will generate an image for you. You can do that all, like there are demos for that within spaces. So the primarily important thing that we can use it for is the models that it gives us and the data sets that it gives us. And so for Hugging Face, there is a Python library. Obviously, there's a Python library that you can use in order to use a train. So you can train each of these models. You can train it on any of these data sets, or you can fine tune it on any of these data sets. You can train it from scratch. You can do all kinds of stuff. It's an extremely diverse platform, and I recommend you check it out outside of this lab as well. And it's all open source as far as I know. Okay. So the goal for today is to fine tune a transform model, and we'll be fine tuning it on. I'm not sure if you guys know there's a dataset called the IMDb dataset. Let me just search here. Maybe it's that IMDb. Yeah, IMDb dataset. So what the IMDb dataset is, it's just a large dataset of movie reviews, and there are positive reviews and there are negative reviews. 0 corresponds to the negative reviews, and 1 corresponds to positive reviews. And our goal is given a review, we want to predict if it's a negative review or a positive review, right? And yeah, so there are 25,000 samples that they provide with labels. And yeah, so we'll use this. And so the code that I'm going to write, I haven't like taken it out of nowhere. I've not written it myself. It's taken from their tutorials itself, and which I can share the link to that as well later on if you need. Right. So what we're gonna do, we're gonna take a transform model. So we're gonna take a transform model and we're gonna fine tune the pre-trained transform model on this dataset called IMDb dataset. And our goal is that given a review, it should predict if it's positive review or negative review. That's it. That's all we're doing today. And that's why I said there's not much coding that we have to do. Let's see if GPU is available. Wait. So we're gonna install a few libraries. So datasets. datasets. This datasets library is from Hugging Face, which is what you can use in order to use all of these datasets. So if you want to use all of these datasets that are provided, you have to use this library that Hugging Face provides, and it's called datasets. Pretty simple name. And there's another model, another library that they provide called transformers, and we'll also import something called Hugging Face Hub, which you can use to like save your checkpoints onto Hugging Face. So Hugging Face or kind of also acts like a GitHub, but for models. And so if you are training something and you want to save your weights, you can save it to Hugging Face. And yeah. So Git LFS, so you know what Git is? LFS means large file storage, if I'm not wrong. So what you do use this is for, so imagine you have like a checkpoint. You know what a checkpoint is, right? So I'm not sure if anybody knows. I mean, everybody knows what checkpoint is. So imagine you're training your model. Imagine you're training your convolutional neural network and you're saving, and you have all the weights. So you have a million weights that you have trained. Now you cannot train it every time that you want to use it. So you have to save these weights somewhere. And say you train it for 100 epochs and you save the weights. And when you save the weights, the weights that you save on your whatever storage, it's typically referred to as a checkpoint, similar to what you have in games. And so if you have a problem, you can resume at the checkpoint. So it's kind of the same idea. It's called checkpoint, and the thing is, you cannot really push like 2 GBs to GitHub, right? And so instead, what you do is you store it on some storage. It can be a remote storage, whatever, and then you have a kind of a pointer to that you save. And to do that, you use this thing called Git LFS. I think it's called a large file system. I'm not sure. Let me search. Large file storage. It's called large file storage. And instead of storing like audio samples, videos, datasets, and stuff, it just replaces that with text pointers, and it loads it lazily. Like whenever you need it, it'll load it from whatever storage. So in our case, we'll be using this to like store it to Hugging Face Hub. Okay. Cool. So once you have so now we have like pretty much all the libraries that we'll be using today. And wait, let me add a section then. So now we need the data. For the data, we'll be using the library that we just imported. So this data sets from Hugging Face. We'll use this to get our data set. So first we'll import function. So our data set is, we can just do load data set and do IMDb. So IMDb is, what am I doing? Yeah. Yeah. So once you pass in, this downloads the dataset for you from the Hugging Face datasets, and then you can use it. It's that simple. I mean, similar to how you did MNIST, if you remember, like similar to that, but then you have like much more variety of datasets that you can use here, and you can just download them and use them within like just a single line of code. Cool. Now we have the dataset, so we can look at it. So we have a train set, which is 25,000 samples, and there's a text and a label. So there's a text, which means the review text, and there's a corresponding label, which says that if it's positive or negative. And there's a test set, and there's also an unsupervised set. We won't be using. I mean, we can use the test set, but we won't be using the unsupervised set because we don't have any use for it. So what we'll do, I mean, we don't need 25,000. We're going to fine tune. So let's create a subset of the train set, similar to how we did in MNIST. We took like, I think, 1,000 images instead of like all the images that they provide. Let's take a small train set, and we'll take the train. We'll take the train set, and from that we'll choose the uh, let's say 3000. So again, I'm not right, like none of this code is mine. I am taking it from uh, I'm taking it from their own tutorial. So yeah, and again we'll generate a test set, and for testing we'll choose 300 samples. So now we have a train set, we have a test set. Train set has 3000 samples, test set has 300 samples. Okay, so one thing that you should have done is shuffled it, because what if like the first 3000 reviews are negative, and then it wouldn't make sense. So like to fine tune, so we should have added a shuffle here. Uh, now it's better. So if you look at small train set, now we have 3000 samples and with a text and label for each sample. Okay. So last time, if you remember for the RNNs thing, once we had the dataset, what did we do? Once we had the dataset, like what did we do? We took the text and we converted it into, if you remember, one hot encoding. If you remember, so like we had say this sentence. Then what you did was you took I, you converted it into a one hot encoding vector. You took A, you took the space, you took M, you converted into one hot vector, and so on. Yes, you can do that manually, but you don't have to, because this awesome library gives you more, gives you classes that will do that for do that automatically for you. So how you can do that? There's something called uh, auto tokenizer, auto tokenizer. And what is tokenization? Tokenization means you're taking the string or whatever input data that you have, and you're converting into the type of data that the model can understand. Right, like last time when we had characters, we converted each of them into a number, and then we converted that to a one hot encoding vector. If you guys remember, like we did that. Instead of doing that, what we can do is we can use this auto tokenizer that is there in this library. It'll automatically convert the whatever data that you're providing, whatever strings, the text that you're providing, into the type that is required by it'll convert into an embedding that is understandable by the model. Yes, somebody had a question, I think. Oh, okay, sorry. Oh my god, that's, yeah. Maybe I'll also share this thing. I forgot. I get forget every time. Uh, okay, so what was I saying? Yeah, right, right. So in order to do tokenization, you do not have to do it manually. You can do it manually, but then this library provides you a class that does it for you. So how do you do that? So you do, let's initialize a tokenizer, which does the tokenization. So from auto tokenizer, from and then you pass in the name of the model that you'll be using, whatever it is. So in our case, what model can we use? So you must have heard about this model called uh, BERT. BERT. It's a big, very big transformer-based language model. It's used for language problems. It was developed by Google. It's a very big model that, and it was like the state of the art on many language modeling tasks for like many years. And by many I mean like 1 or 2 years. Uh, and we won't be using this because it's super big. What we'll be using is something called, wait, that is what they've used in the tutorial as well, distilbert. The distilbert is a distilled version, meaning it's a slightly smaller version in terms of number of parameters, and it's a distilled version of BERT, and it's enough for us in our use case, because like we are gonna fine tune it on like 3000 samples, so we don't need the biggest model in the world for to do that. So we'll be using this distilbert uncased model. Uncased meaning that does not focus on the case of the text. So you'll be using digital BERT base uncased. If you run this, what happens is it automatically looks at the model and it automatically chooses a tokenizer for you. You do not have to, bust your brains like doing one hot encoding or whatever kind of embedding it is. It'll automatically do it for you. Okay. So now that you have this, now that you have your tokenizer, you need to apply it to the data. So how do you do that? So we'll write a function for that. It takes in a few samples and it applies to each of these. So So what this function does is it takes in a dataset or a sample of the or a subset of the dataset. It takes in and then it applies this tokenizer to the text in it. We do not want to apply to the labels. We only want to apply to the text in it. So you apply it to the text, and truncation equal to true means that. So you remember how we like padded. How we padded. You remember, right? We took the longest sentence and we padded all the other sentences to that same length. Or there are different kinds of truncation that you can do. That is one kind of truncation, but yeah, truncation basically means like making it the same length, as far as I know, or it means cutting short. I'm not sure what its exact like grammatical meaning is, but yeah. Right. So we can generate now. So now that we have a function that applies the tokenizer to the dataset, we'll apply the tokenizer to the dataset. So we'll take our small train dataset and we'll map to that this function that we just made, preprocess function. And we'll do the same thing for the test dataset as well. Small test dataset. We'll map the preprocess function. Okay, there's a flag that we have to set. Batch parameter. Batch is equal to true. Just means that you want to batch it. So that is for the map. So this map. So it's like these are all like small functionalities that's provided by the library itself. So what you do is you take the so it'll map this function onto each batch within the dataset. That's basically it. Why is it saying that this does not exist? Small train set. Okay, small train set. And then we'll save this as tokenized train. Tokenized the test as well. Okay, so that's done. Okay, so now once we have the data in the representation that we want, we need to we can just pass that to the model directly. The model expects PyTorch tensors, and to convert it to PyTorch tensors, we use something called a data collator. It's called data collator. You can implement this yourself, or or you can make use of the thing that's already implemented in Hugging Face. So let's again import. So I have to remind you that I'm not pulling this out of nowhere. Like I haven't like by hearted all of these things. That's just like look at the documentation. There's like you will see like what kind of functionality is like implemented in the auto tokenizer. What is there, and so even within the transformers library itself, there's like huge amount of functionality that's implemented. And if you look at like other people's code, you'll realize like what all stuff you can actually do. Yeah, data collector with padding. So what this does is it automatically takes the data, whatever the representations that you generated, and it converts it into PyTorch tensors and concatenates them. So once we want to make a batch, you remember like if we had like a 2256 by 256 image and the 256 by 256 another 256 by 256 image, then you concatenated them to get a 2 by 256 by 256 image. So it does all of this automatically. So it converts it into. Just give me a second. Let me drink some water. Yeah. So instead of doing this manually, there is a functionality within the library. So you just take this thing, a data collator with padding, you apply it. So so the collator itself, you do not apply directly to the thing. You will pass it later on to there's something called a trainer that trains the model. You'll see. I mean, you'll see. Wait, and this is our data collator. So now we have everything that we need to train the model. So we'll actually train the model, right? so so right now we have the data. Using the tokenizer, we convert it into the representation that we want. Okay, we convert it into the representation, whatever representation it is that we want. And then you have a collator that is, declared a collator, you didn't apply it yet. You declared a collator that is going to convert the data that you have into PyTorch tensors, and it will also concatenate them so that it's you can then just do a forward pass through the model. So now you can train the model. So for that we need a model. So for that we'll first import. So again, you'll see like how easy it is to do this. So you import auto model for sequence classification. Yeah, this thing. And so what this does is, so when you pass in Distilbert base uncased to this, it will take that model. Okay, it will take that model and it will automatically generate a model that you can use to do sequence classification. That's what we're doing, right? We are passing in a sequence of text, and it is classifying if it is positive or negative. And so you do not have to add like all kinds of so you do not have to add a fully connected network at the end that is going to reduce the dimension to like 2, and then you apply like all that kind of stuff. You do not have to do. And so what you can just do is you can do auto model. I'm not typing this again. For classification dot from pre-trained Dilbert base uncased. And how many labels are there? There are 2 labels. And again, I have to remind you, you do not have to remember any of this. Like none of this code is actually you do not have to remember any of the stuff. And I'm not going to ask it in the quiz either, because like it's not really important. You just have to have an idea of what actually is happening. Like what are you doing with all these functions? The actual functions you don't have to remember. You can just look at the documentation and figure out what you need for your particular use case. So what you've done, made a model that is going to do sequence classification, and what is the base? The base model for that is Distilbert base uncased. And so, and how many labels are there? There are 2 labels, positive or negative. You run that and it'll download the pre-trained weights, I guess. Whatever this Distilbert base uncased has been trained on. I'm not sure what it has been trained on. We can check that, I guess. It has been trained on Wikipedia dataset and Book Corpus dataset, which are 2 big datasets. That is what has been used to train the thing. And so, I mean, you cannot take an untrained model and train it on 300 samples and expect it to work. So you take a model that has already been trained on like a huge corpus of text, and you fine tune it to whatever you're trying to do. Okay, so it has downloaded the model. So the model is ready to use. So now what we need, we need some way to report metrics. And what is a metric that you can use? A metric that you can use, I mean, for instance, fund score, accuracy, etc. Right, all of these you can are metrics that you can use. And again, no surprise here. Again, you do not have to implement this. It's already available in. Okay, that's not what I want. It's already available in datasets that is provided to you by Hugging Face. It's already implemented. So if you import, so something called load metric, and you can just pass in whatever metric you want. So if you want accuracy, you will do load metric accuracy. If you want F1 score, you'll do load metric F1 and so on. Okay, so let's define a function that will compute metrics for us. Metrics for us, which takes in a tuple. And what it does is, so let's first load the actual metrics themselves. Load metric, you just call load metric on accuracy, and on F1. So let's say these are the 2 metrics that we're using. And again, let's go to the documentation. So there are like huge amounts, different variants of where is it? There means somewhere loading a metric. Okay. Yeah, so like there are different metrics that you can do. All of these, I guess. No, there should be more. I mean, yeah, just go through the documentation, figure it out yourself. So, yeah, so there's different metrics that you can do, and F1 as well, F1 score. And once you do this, you have a object that will compute accuracy and that will compute F1 score respectively. And all you have to do is you have to call them on your whatever data you're getting. So now this eval prediction that you're passing in is a tuple. So you'll unpack the tuple. Basically, there are two things inside the tuple. So this logics correspond to the output of the model, and the labels correspond to the labels. There's no. So logits means the raw normalized scores. That's, I mean, you it's another name for that. So wherever you see logits, it means that you're not applying a softmax. It's the direct output that you're getting from the model with the prior to any normalization or something that you do. That's called a logits. And the labels are the corresponding labels to ground truth labels that you want. And you unpack this from this eval prediction. So if it's a tuple and there are two values, you can just use this. Okay. And now what you're going to do, and what are the actual predictions? So if you remember, we used to use argmaths. That's exactly what we're going to use now. It's also so argmaths. What does argmaths do? Argmaths looks at the predictions, and it determines at what position is the maximum value at, and it returns that position. So if it's at position 0, it will return 0. If the maths is at position 1, it will return 1. And what does that tell us? It tells us that the model is predicting that it's a positive review or negative review respectively. Okay, so now you have your predictions, which are 0, 1, 0, 1, 0, 1, so on, and you have a label 0, 1, 0, 0, 1, 0, 1, and so on. And using this, you can calculate your accuracy and F1 score. So accuracy, you have the object already that you've created for load accuracy, and you can just call dot compute. Dot compute will calculate it for us. So you pass in the predictions, you pass in the labels, references, yes, labels, and this will calculate the accuracy for you. And so for some reason they've decided to pack it into a dictionary, so you have to yeah, and load F1. Again, same thing, so I'll just copy that. I'm not in the mood to type it. And then again, it's in a dictionary, so you have to pack it, right? And then so now you have your accuracy and your F1 score, and so you'll return a dictionary with accuracy. Accuracy. Oh, okay. I could have just, what am I doing? Yeah. In retrospect, I could have just joined the two dictionaries, but yeah. Yes, so now you have a function that will compute metrics, and you're not going to do it manually. You're going to just pass this on to a trainer that you'll see later. What this trainer does is it will automatically take in your compute metrics, your model, your data collector, your tokenizer, all of this it will take, and it will do everything for you. Just don't do anything. It will do everything for you. Like it will take in the data set also. It will train it and it will give you the model, the train model, and it will evaluate also for you. Everything will be done by itself. Yeah. So now you have a function that you can pass in to your trainer that will calculate accuracy and F1 score given your predictions and the ground truth labels. Okay, so now that we have done all of this, we are pretty much ready to train. Okay, and so before we train, if you remember, I told you that we can use Hugging Face as kind of like a mm, kind of like a GitHub for models, where you can like save your weights, you can save in your models and configuration files and all that kinds of stuff. And for that, I mean, with GitHub, you have to log in to Hugging Face. So we log in to Hugging Face. So we imported Hugging Face Hub notebook login. Is a it's the functionality that they provide that you can use to log in uh, to Hugging Face, your Hugging Face account from your Jupyter notebook itself. So if you run this, they are asking you to copy a token from your account and paste it here. So you can just go to settings and go to access tokens, and you can create a new token by clicking this. I've already made a token for the lab, so I just copy that. I'll go here, I'll paste it, and I click login. and I'm done. I've logged into Hugging Face, and now I can push all of my stuff, all of my checkpoints or whatever it is to Hugging Face. Okay, so we have everything. Everything is ready now. All that we have to do now is to train the model. And how are you going to train the model? You're going to train the model using something called a trainer, which is also provided by Hugging Face. So we're going to import something called trainer, which you can use to train any model. And you also need some called training arguments, which you will specify the training arguments in. So first, let's make the training arguments. Training arguments. And where do you want to save it? You will save it in tuning sim model. Save it in this folder, so it will be the repository within the Hugging Face. So similar to how you have repositories in GitHub, you have repositories here as well. And yeah, that's it. Right, and our learning rate, you can specify learning rate here, 2e minus 5. That's what they have used for some reason. I don't know. Yeah, so typically when you're fine tuning, you do not use big learning rates because you do not want to like mess up the entire weights that are already pre-trained, because initially there will be like huge gradients that happen. Because so what happens is you have a pre-trained model, and this pre-trained model has not been trained on whatever you're going to do. So if you directly use like a huge learning rate, and there'll be huge gradients due to backpropagation, there'll be huge gradients that are generated. And if you have like a huge learning rate, like I don't know, 0.01 learning rate, then what happens is like big steps, like optimization steps will happen, and that like mess up what you're trying to do. So what you do is you use a small learning rate at least to start with during your fine tuning. And yeah, so this is a pretty small learning rate that you can use. That's probably why they have used it. I'm hypothesizing at this point, but yeah. Device train batch size. So in our case, we only have one GPU, but in case you have multiple GPUs, they'll handle it. The device eval batch size also will set it to 16. So the batch size that we're going to use during forward pass for the training step and the evaluation step. How many epochs you're going to train for? 2. Weight decay 0.01. I don't know if you guys know what weight decay is. I'm not sure if sir must have covered it. I mean, it doesn't matter. It's a hyperparameter. Who cares? Save strategy. So you save it after every epoch, or you iterate over epochs to save it. And then do you want to push it to the hub? Pretty much it. So you're just creating a object that stores all of this training arguments, and then you're going to pass it to your trainer afterwards. Okay. This, and now you're going to create a trainer that will take all of this and train your model. So your trainer, what all does your trainer take? Your trainer takes a model, actually. The actual model that you're going to train. It takes in the training arguments that you just made. Training arguments. It takes in the dataset. It takes in the test dataset, eval dataset. Equal to tokenize test. It takes in the tokenizer that we made. It takes in the data collator that we made. Data collator. And it takes in the metric, compute metrics function that we made that will compute the metrics and report it to us automatically. Okay. Did I make a typo? No, I did not. Okay. So, yeah. So now your trainer is ready. Everything is ready. So if you look here, I'm not sure if it's there, but let's see. Yeah. So now this, repository has been created of this / fine tuning sentiment model. And so whenever you push stuff here, it'll automatically come here. It's kind of like GitHub only. Okay. So now we go back. Everything is done. So once you have trainer, it's as simple as this, just doing trainer.train, and it'll train the model for you. Given all these like stuff that you've passed to it, it'll automatically do everything. No need to write like a whole training loop and all that stuff that you used to do, optimize the dot step, nothing, just. And this is going to take 4 minutes. So if you guys want to take a break, now's the time. I mean, there's not much after this as well, but then if you want to take a break, now's the time, because there's nothing to do during these 4 minutes. So once this is done, if you call trainer dot, so you call trainer dot train right now. So we call trainer dot evaluate. It will evaluate on the evaluation set or the test set that we had specified. Will evaluate the train model on this using the metrics that we had given. Right. So we got that the evaluation accuracy is 86% and the F1 score is 86.8655. And so that's for evaluation. So it automatically evaluates on the whatever test set that other evaluation set that we had given, passed to the trainer. So if you remember, we passed to the trainer evaluation set here, the tokenized test, and that will automatically evaluate for you. So now once you're done with all of this, you want to push to the hub. You want to push to the Hugging Face hub. So how do you do that? Again, it's that simple. Just do trainer dot push to hub, and that will save the what do you call the thing? Yeah, so the checkpoints, the model configuration files, all of it will be automatically saved onto this. And again, this is going to take 4 minutes, I think, but then we'll keep on discussing this part. So like once you have a train model, so once you have a trained model and you want to manually pass in input to it, to the model. So what do you do for that? You need something called a pipeline. And again, code pipeline and you can take this pipeline and pass in your model. So in my case, it will be this. Oh my god, copy. Yes, I can pass in the model to the pipeline, and it will create a pipeline for me. Sentiment model. And once it's done, all I have to do is I have to just take the sentiment model and pass in a variable number of input. So in our case, we'll pass in a positive review and a negative review. So a positive review will be like, this is the best movie I have that I have ever seen. And a negative review would be what? Very polar reviews. And if we pass this, then hopefully it should give us the labels corresponding to a positive review and a negative review. Now the thing with pipeline is that you can have like multiple models back to back. So like imagine you pass through a model, pass some input to a model, and you get an output, and then you can take that output, you can pass through another model, and so on. Like it's very versatile what you can do with it. 2 more minutes. No, I guess, yeah, 2 more minutes for this to push to the hub, because like this huge weights, right? So like it's uploading the weights onto Hugging Face Hub. Now the funny thing is now when I'm gonna call pipeline of this thing, it's gonna download those same weights. But yeah, should be much faster. Yeah. So it's finished pushing all of the configurations files and checkpoints to the hub. Now it's creating the pipeline, and the pipeline is done, I guess. Great. And then now we'll call the pipeline that we made on two reviews that we wrote. So positive review and a negative review. So corresponding to review one. First review, we got a label 1, and corresponding to second one, we got a label 0. So label 0 is a negative review, and label 1 is a positive review. And the confidence or the corresponding score is 0.97 and 0.94. So it's pretty confident that this is a negative review and that this is a positive review. Now, the amazing thing is that now if you go to if you go to your repo on Hugging Face, it has a inference API that has like automatically generated for you, wherein you can enter, and it will run this input through the model on the cloud, and it will give you the label, corresponding label, whatever it is. Yeah, so and it also like has like information about the model, its fine-tuned version of Distilbert, and the accuracy, the furnace, all this on the IMDb dataset. Right. So now it's saying that it's label one with 96.5% confidence. It says that it's label one, which means it's a positive review. I mean, yeah, it's positive label. And you can do this with other people's repos as well, assuming they have this enabled. If they don't, you can't. But if they have it enabled, you can run pass inputs through other people's models. You can do all various kinds of stuff. So it's kind of like GitHub only in the sense that it has to be public. If you have to do that, you can also private this, as far as I know. Yeah. Right. So that's pretty much it in the case of sentiment analysis. So that's NLP, and you can do computer vision as well with transformers. So there's a variant of transformers called vision transformers, and like others, maybe like others at this point I think like hundreds of different models that have been built upon vision transformers, and you can use those to do all kinds of tasks that you would use a convolutional neural network typically. So for instance, semantic segmentation, object detection, or like whatever kind of computation task that you want to do, you're now able to do that with transformers as well. And so if you go to models, and if you go to VAT, okay, these are the most popular. Yeah, this one. So this is the original VAT. So you can pass in like a image, and it'll classify it for you. It says that it's a tiger, and specifically the species. I hope this is a species name. I'm not sure. Uh, you can do that as well using transformers, and for that, there's like a very specific kind of thing that you do, wherein you first take the image and you split it into patches. And so, like in case of NLP, or in case of natural language, you have like text, right? And this text is sequential by default, like vision transformer model. So it's like there's an order to it, and it's a sequence by default, right? But in case of an image, how do you make it a sequence? Like it's not a sequence, right? It's a two-dimensional. In fact, it's a three-dimensional tensor. So for that, what you do is you first. I mean, if you remember how like uh, there's something called a sliding window, right? I'm not sure if you guys know, but like kind of like you take a patch here. So imagine you take this and you split it into 4 by 4. So 4 by 4, and then you have 16 patches. And what you do is you take those 16 patches, lay them out, like lay those patches out, so that it'll be a single sequence of 16 small images, right? Like this image, this image, this image, this image, this image, and so on. So then you have like a sequence of 16 images, 16 small patches, and then now you have a sequence. So now once you have a sequence, you can apply transformers to it. That's all that they've done in vision transformer. Like they've played around with it, like uh, they've done like yeah, so that's pretty much the basic idea of vision transformers. Like the main idea is that because you do not have a sequence by default in case of images, you generate a sequence. And how do you generate a sequence? You generate a sequence by splitting this image into patches. And because now once you split it into patches, there's a fixed order that you can have. Like you can have this first patch, then this patch, then this patch, then this patch, then this patch, and so on. So you have a patch of 16 tiny images, and then you can apply a transformer on it. Like you can then have maybe take each patch, generate a pass through fully connected network, and generate a k sized vector from it. So that will be our x1, and then pass this through an MLP, and then you get a k size h2, and so on. And you take all of them, and then you pass it through a transformer, and so on. And so wait, so important thing that I have to mention is that, so this is the original paper for the transformer architecture. This is the paper that introduced the transformer architecture, and so in this paper, yeah, so it's from 2017. It's been like 5 years now. So in this paper, they have so the architecture that they have done here is not really important, because this is not a transformer right now. Like you do not have to do this to call your model a transformer. All you have to do is what I told you earlier, wherein you have to have a self attention and the MLP, self-attention, MLP, self-attention, MLP, and so on. And but then in this paper, so typically you can implement it such that you have an encoder and a decoder. That is what they've done here. So in case of in case you're doing natural, I mean, like say translation, you're doing translating from English to French, and in that case, you'll use the encoder to encode it, and then a decoder to decode it to French, and so on. So you can have an encoder decoder type of model with transformers, but it's not necessary. All that's necessary is that you have a multi-headed attention and you have a fully connected network. Feed forward means fully connected network. And so like presently, like nowadays, if you look at models, you can see that there are encoder only models. You can have an encoder and a decoder. It doesn't really matter. All that it has to have, and I'm like laying this out because it's important. All that it has to have is self-attention and potentially an MLP as well. So it has to be alternating layers between a self-attention and MLP and self-attention and MLP. So you can think of it as you're generating. Yes. So it depends, because if you are dealing with images, yes, it is important. It is important because you remember that I told you that the positional thing is not completely solved. Wherein like Abhijit chicken biryani and chicken minita with biryani, that thing is not completely solved even when you're dealing with MHA, multi-head attention. So if you really want to solve it, what you can do is you can encode some kind of positional information also to the token, saying that, oh, this token is at first position, this token is at second position, and so on. But then the thing is, that's not really, that's just a trick that they use to work around some of the downsides of transformers. But then it's not a key component of every transformer model out there. Yes, please. It depends because it also depends upon how much data you have. In case you have 1,000 images, I would not recommend using a vision transformer, because usually vision transformers need huge amounts of data, and they, I mean, they might be more efficient, but they still need a huge amount of data in it. Like you probably can't train it, and it's tricky to train it because it's very dependent on the hyperparameters as well. You must have observed this with convolutional neural networks, wherein like you do anything with convolutional neural networks and it just works, because like inherently convolutional neural networks have an advantage when it comes to computation tasks. But that's not the case with vision transformers. You have to explicitly, like, you'll have to find the fine tuning is more important when it comes to vision transformers, or transformers in general. The fine tuning aspect is more critical there. And so if you are dealing with a toy sized problem, then it's typically a good idea to just use convolutional neural networks. But in case you want to, I don't know, publish a paper, then it's probably a good idea to do transformers. Plus, if assuming you have the computational resources for it, because it's not you're not going to train it on your CPU anyway. And yeah, it takes some beef to train it. It's not really beefy GPUs, I mean, to train it. So yeah. So it depends upon your problem. That's the answer. Right. And so what did I mention? Yeah. So there are models with encoders and decoders, and that's not necessary. You can have encoder only models as well. This is so basically what I'm saying. There's a huge variety of transformer models. I encourage you to go out and read a few papers on transformers. Like even this year, like in conferences, if you look at that, like I even saw an article saying that, like, even on LinkedIn, you must have seen like the people saying there are 200, 300 papers on transformer based papers this year, and here is a repository that summarizes them. So you'll find that kind of stuff. So it's that widely used nowadays, and even in production, it's very widely used. And even I think if you do when you do like Google Translate, I think it's the transformer model now. Yeah. Yeah, so that's about transformers. So just understand that you can apply to NLP vision and whatever you can think about, because these are in the end, these are functional approximators, and you're training them to produce an output from some kind of input. And in case of transformers, they are capable of much more, but then it's also much more harder to make them do that. Yeah, and they're also very versatile, so you can apply it to all kinds of problems. Right. So that's pretty much it for this lab. Like, this lab is pretty much shorter because we didn't write like entire training loops and stuff like that. Next lab we'll have to, when we're dealing with GANs, we'll have to do that. But this today we just dealt with a pretty well made library. So like there was very little thing that we had to write. And yeah, So yeah, so this lab is done. So now what I will do is I'll share the. I had it saved here, but yeah, I'll share the form for the quiz. Not this one. Um, yeah, this is a pretty amazing blog post. It's like it makes it so easy to understand what's happening. Even when I first I was very confused with the so when you read the attention is all you need paper. I mean, I was very confused. Like I couldn't figure out a lot of stuff. But then when you read this blog post, it's very, very, very well written, and it'll give you an idea of what a transformer is. Like with none of the extras. Like the basic idea of what a transformer is. I mean, you have to keep in mind that it's 3 years old, and modern transformers do a lot of extras, and so but then you'll get a basic idea of what a transformer is and why it works. Okay, so quiz. It's a pretty short quiz. You'll probably be done in 5 minutes, but because there's no. Okay, I think let me just check the settings before I send it. Great. It should be again 15 minutes. You won't need 15 minutes, but it's 15 minutes. But okay. So I'll close it at like around 52, which is 352, 353, around. Yeah. So you can start writing now.